what do we need? We need some examples. 103 times 105, 106 times 102, 101, 107, 102, 109, and then we need some answers. 10815, 10812, and then we probably also want some under examples. 93 times 97 times 93. Let's see, what is that? 9021, 5 and 9, 45, 66, 83, 66. All right. Oh my gosh, that took 5 minutes all by itself. I need to be done in about 6 minutes. Can I do it? Almost certainly not, but maybe. So I just can't quit messing about with the distributive property. I'm sure this is an experience we've all had from time to time. I want to leave it behind. I'm planning on something else. I want to talk about the fundamental nature of multiplication with you. I want to talk about positives and negatives, how we multiply them, why the products are what they are. But there was just one other thing I thought of, and I think this is going to be the title of the video. How do we make a math trick? So we've looked at several different tricks over the last, 5 videos or so, and we've been using the distributive property. But who thought up these tricks in the first place, right? Where did they get them? What did they do? How did they generate them? And one thing you might expect is, I bet someone just sat down with a list of numbers, multiplied them out, and just kind of started noticing patterns. And that is a good step one. If I were at all good with video, I'd say step one, notice patterns. That is a good thing to notice when we want to start to develop a math trick. So for example, I've got a bunch of stuff, a bunch of the under 100 and over 100 tricks that we have talked about again in the last several videos. The over 100 trick, just over 100 trick, you might list out a bunch of products. 103 times 105 is 10,815. 106 times 102 is 10,812, etc., right? And then you might just start noticing, the 3 and the 5 have a sum of 8, but a product of 15. The 6 and the 2, sum of 8, product of 12. The 11 and the 4, sum of 15, product of 44. And so you might look at that and think, okay, so I'm just going to invent a trick where if I take, say, 103 times 107, I'm going to take the sum of the 7 and the 3 and write it down, and then the product of the 7 and the 3 and write it down, and I just happen to notice, they all begin with 1. So there it is, we've developed a math trick. And that's good, but we don't quite understand why this works. And of course, last week, again, I looked at you with why it does work. But what if we hadn't noticed the pattern, right? Or again, I have some other examples over here of the just under 100 trick instead. Now I have gone ahead and written in the just under 100 part, because this one is not quite so obvious. 93 is 7 away from 100, 97 is 3 away from 100. But looking at that, you can see, okay, so the 7 times the 3 is where we get the 21. 95 is 5 away, 91 is 9 away, 5 times 9 is 44. 2 times 7 for this one, 14. 89 is 11 away, 94 is 6 away from 100. Product is 66. It might be getting a little bit harder to see, wait, are these also sums of some kind? And of course, hopefully what happens is you realize, they're not sums. Instead, they're differences. And we said in our video there were a couple different ways to think about these differences. You could just take this digit and subtract how far away that is from 100 from the other number. So 7, we've already said, is 3 away from 100. 3 subtracted from the 3 is where we get the 90. 9 is the difference between 91 and 100. 9 subtracted from the 95 is where we get the 86. I mean, that's definitely true. That is what's working here. But obviously that's a lot harder pattern to pick up on than simply the sums. And so I want to show you, I don't know who first developed these tricks. I do know. His name was Sam McFanus, and you don't want to mess with him. So I don't know who developed these tricks first. I don't know if this is precisely what they did, but I think I can more accurately describe what they did, and in so doing, describe how we can invent our own math trick, which is the goal of this video. We are going to invent a math trick today. Okay, so here's what this process looks like. Let's take numbers just above 100, but instead of calling it like 103 or 105, I'm going to call it like 100 and blank, something just above 100. And I want to multiply it by another 100 and blank. But 100 and blank isn't super easy to work with mathematically. Instead, I'm going to introduce a variable. I'm going to say, well, let's just call it 100 plus a. And so that's going to be the first number here, 100 plus a. And then the second number, let's call it 100 plus b. So it's going to be some different number just above 100. And we're just going to kind of write over here in the margin, a and b are small. If we need to define small later, we will. Right now, we'll just say they're small. And we're going to bring back the box, everybody's favorite tool for analyzing this stuff. And we're going to put our 100 plus a across the top. Doesn't really matter where, but we'll do it across the top. 100 plus b down the side. And let's see what's going on here. Well, we know, of course, 100 times 100 is 10,000. So that's where we get the 10,000 from. 100 times a would be plus 100a. 100 times b would be plus 100b. And then a times b, remember we're finding the products in these different boxes, a times b is just ab. So if we write this out, we get 10,000 plus 100a plus 100b plus ab. Now if you're remembering the trick, 3 times the 5, that's that product AB. So that's why it's ending in 15. For 103 times 105, that's why we end up with a 15 at the end of that particular answer. The middle part is a little bit weirder though. But if you think back to what I said about multiplication last week, that the very different algorithms for multiplication are actually just different ways to combine single-digit products with place value, this is kind of a place value thing going on here, because another way to write this 100a plus 100b is actually just 100 times the sum of a and b. Because I can almost see the distributive property here in reverse, right? Imagine taking 100 times the product a plus b. We normally send that 100 in, and so we get 100a plus 100b. But it's just as possible for us to do this process backwards. Let's take the 100 out of each expression, and what gets left behind? The a plus the b. So that's what this is right here. And now it should start to become a little bit more clear here. Oh, we're going to take the 3 and the 5, and we're going to add them together. But we're going to put that sum in the hundreds place. Now, it might be a 2-digit sum. So when we talk about the hundreds place, it's really the hundreds and the thousands, right? That was not the case here. In this case, 3 plus 5 is just 8, and we take up the 2 spaces. But you'll notice in terms of the overall number, of course, the 10,000 we know is just coming from, or the 1 rather, is just coming from the 10,000. The 8 has to be in the hundreds place because of this 100 over here. So that's 815, right? 10,815. And so we can use this box not only to understand tricks, but actually to invent new ones. Okay, so that was a little explanation of how we develop a math trick. Tomorrow, because I'm realizing I'm not going to have time to do it in a single video, tomorrow I'm going to look with you at how we would develop a new math trick, one that we have not yet looked at. We're going to try and multiply a number just under 100 by a number just over 100. So please make sure to come back tomorrow, check out that video, and yeah, if this is helpful to you, if you like this, like and subscribe, tell your friends about it, and I will see you around. Okay.